What specific problem does the proposed method MCT aim to solve in the context of diffusion models?
The proposed method MCT aims to solve the problem of efficient sampling from diffusion models by distilling a pre-trained diffusion teacher model into a deep latent variable student model. This student model enables efficient generation by mapping from noise to data in just one step, thus reducing the computational cost of sampling from diffusion models. MCT specifically addresses the challenge of reducing the number of steps required to produce samples while maintaining high-quality results, especially in the one-step generation regime. By minimizing an approximation of the mode-covering divergence between the teacher and student models, MCT aims to capture the full distribution learned by the diffusion model and enable real-time generation applications. The method leverages an EM framework that alternates between estimating learning gradients with Monte Carlo samples and updating the student model through gradient ascent, ultimately improving the efficiency and effectiveness of sampling from diffusion models.
How does the proposed method MCT work, and what are the key steps involved in its operation?
The proposed method MCT works by distilling a pre-trained diffusion model into a deep latent variable model through an EM framework. The key steps involved in its operation include 1. Initializing the student model with the teacher model weights, 2. Running Langevin dynamics with joint sampling of noise and latent variables to correct the sampled pairs towards the desired distribution, 3. Canceling accumulated noise in the samples to improve the stability of training, 4. Optimizing a weighted loss over all noise levels of the diffusion model to match the marginals of the student network with those of the diffusion process at all noise levels. 5. Employing alternating updates for the generator and score networks. 6. Leveraging reparametrized sampling to accelerate joint MCMC sampling and simplify step size tuning. And 7. Flexibly interpolating between mode-seeking and mode-covering divergences by adjusting the sampling schemes. These steps collectively enable MCT to efficiently learn a one-step student model that outperforms existing approaches in terms of FID scores for image generation tasks like ImageNet and text-to-image generation.
What are the theoretical or practical benefits of using the MCT method compared to existing approaches for diffusion model distillation?
The theoretical and practical benefits of using the MCT method compared to existing approaches for diffusion model distillation lie in its ability to efficiently distill a pre-trained diffusion model into a deep latent variable model with a single-step generation capability. The MCT method minimizes an approximation of the mode-covering divergence between the teacher and student models, enabling efficient generation by mapping noise to data in just one step. This approach reduces the computational cost during training by running multiple sampling steps per iteration, which can lead to faster convergence and improved performance. Additionally, MCT leverages the EM framework with novel sampling and optimization techniques, allowing for the learning of a one-step student model whose marginal distributions match those of the pre-trained diffusion model. This method outperforms existing approaches in terms of FID scores for ImageNet 64 and ImageNet 128 conditional generation, as well as in text-to-image generation tasks. Overall, MCT offers a more competitive and effective solution for distilling diffusion models into one-step generators, showcasing strong performance in various generative tasks.
How is the method MCT validated or tested in the paper?
The method MCT is validated and tested in the paper through empirical experiments on ImageNet 64, ImageNet 128, and text-to-image generation tasks. The paper compares MCT with existing approaches for one-step diffusion generation, showcasing its competitive performance in terms of Frechet inception distance, FID scores. The experiments involve training the student generators with MCT using a varying number of Langevin updates, ranging from MCT1 to MCT16, and evaluating their performance based on FID scores, inception scores, as recall and clip scores. The results demonstrate that MCT outperforms existing methods for one-step distillation of diffusion models, achieving strong performance in image generation tasks. Additionally, MCT is tested on text-to-image models by distilling the stable Diffusion v1.5 model, showcasing its effectiveness in image generation from text prompts. The paper also discusses the impact of key components of MCT, such as noise cancellation, multi-step joint sampling, and reparametrized sampling, on the overall performance of the method. Through these experiments and comparisons with existing methods, the paper validates the efficacy and competitiveness of MCT in one-step generation tasks.
What results were achieved with the MCT method in terms of ImageNet, conditional generation, and text-to-image generation?
The MCT method achieved impressive results in terms of ImageNet conditional generation and text-to-image generation. Specifically, for ImageNet 64 and ImageNet 128 conditional generation, MCT outperformed existing one-step generation approaches with FID scores of 2.20 and 6.0, respectively. Additionally, MCT performed favorably on one-step text-to-image generation by distilling from stable diffusion models, achieving a FID of 9.66 for one-step text-to-image generation. These results demonstrate the effectiveness of the MCT method in generating high-quality images and bridging the performance gap in one-step generation tasks.
What are the limitations or drawbacks of the MCT method as highlighted in the paper?
The limitations or drawbacks of the MCT method as highlighted in the paper include the following points. 1. The MCT method requires the student model to be initialized from the teacher model to perform competitively, indicating sensitivity to initialization. 2. Empirically, while theoretically possible, training a student model entirely from scratch did not yield competitive results, suggesting limitations in training from random initialization. 3. The method introduces additional computational cost during training due to running multiple sampling steps per iteration, impacting training efficiency. 4. The step size of the MCMC sampling process in MCT requires careful tuning, adding complexity to the training process. 5. There is a fundamental trade-off between training cost and model performance, indicating a need for further analysis to optimize this trade-off. 6. The paper suggests future work could focus on enabling generation from randomly initialized generator networks with distinct architectures and lower dimensional latent variables to address limitations in initialization sensitivity. 7. Improving methods to achieve competitive results without relying on teacher model initialization is an area for potential enhancement. 8. The sensitivity to the choice of T***, fixed time-step conditioning, at initialization is highlighted as a limitation that could impact the method's performance. 9. While MCT demonstrates strong performance in certain tasks, there is room for improvement in terms of training efficiency and model generalization. 10. Future work could focus on analyzing and enhancing the trade-off between training cost and model performance to further refine the MCT method.